Okay, so I've set up a bit of a question there about rotating 1, 4 by 90, 180 and 270 in an anti-clockwise direction. I want to know what the associated matrices of transformation are, but let's first decide what the actual coordinates are. Can you tell me the rotated coordinates of point 1, 4? It is important to recognise here, and I haven't put it down, that I want to rotate about the origin. You don't have to rotate about the origin, but in fact our rotational matrix will always be about the origin. If you wanted to rotate about the point, say 2, 2, then you would first translate your point so that it's at the origin, i.e. add -2 on, and then do the rotation, and then you'd add the 2, 2 back on. That's how you do that rotation. But nonetheless, let's just talk about a simple rotation first by 90, 180, 270. Does anybody know any of those coordinates? -4, 1 is here. Is that one of the coordinates?
Yes.
I agree. Good. That's a bit of a curly one.
4, 1.
4, 1? 4, 1 is here. Is that one of the...
That's not okay. That's definitely not
-1, -4.
-1, -4 is here.
180.
Yep, I agree with that.
And then 4, -1.
4, -1, which is about here. Good. Yep.
4, -1.
That's that.
Is that cool? Okay. So how could we get from, let's just start with a 90 degrees rotation. How could we get from the coordinate 1, 4 multiplying by a 2 by 2 to give us -4, 1? What would be the matrix multiplying? No, so you're reading ahead at the moment. I want to know, I'm trying to build an understanding rather than just reading what the answer is. What matrix? There's an obvious matrix here. This is actually just a series of reflections that you could build. So where do you think that -4's come from?
0, -1.
Oh, well then it's 0, 1, 0.
No, I beat 2 and I already said it.
I hate you.
0, -1. What's the second?
1.
1, 0.
1, 0. So from our work with deflection, you'll note here that 0, -1 will take this, it will cancel out that 1, and it will provide -4 in the top. And then 1, 0 will give us the 1 here and then cancel out the 4. Yeah? So you can see that we could develop that understanding, and it works nicely for 90 and 180 and 270. So equally, if I was doing 180, 180 takes us to -1, -4. Hopefully you can see this is just -1, 0, 0, -1. And the next one is something times by 1, 4, and that will take us to 4, -1, which again hopefully you can see is 0, 1, -1, 0, yeah? Okay, so Xander has touched on the relationship here, and that is that a rotation can be based on the angle that you're rotating. So let's talk about this a little bit, and there's the general form. And I've got this that does this work above, and we'll have a look at that in a minute. In green down here, just as a quick note, this is proven in the text, but it uses topic 2 of unit 2, and we're not doing topic 2 until early next term. So I'm not going to go through the proof, but you're welcome to have a look at it. It uses topic 2 in that topic 2 introduces some theorems, some further trig theorems, and it just quotes them in there. So it won't harm you to have a look at it, but that's what it does. So if we have, generally speaking, this is the diagram that they use. If you want to rotate from P, X, Y, from the origin around theta in an anti-clockwise direction, that rotation can happen based on this rotational matrix. And I can't remember if this is on your formula sheet. I feel like it might be. But that happens based on that rotational matrix, cos theta, -sin theta, cos theta. And so in this case, if theta was 90, then we'd have cos of 90, which is 0. Sine of 90 is 1, but that's -1. Sine of 90 down here is 1, and so that stays as 1, and then cos of theta is 0, we get 0, -1, 1, 0. And that's our rotational matrix. So those trivial 90, 80, 180 and 270s that we could work out, they still exist and work, but we can also do now rotation by 30 and 45 and 128 or whatever, just by substituting those angles into there. So let's have a look at an example where we're rotating an isosceles triangle 45 degrees about the origin, given its vertices 2, 1, 1, 4 and 3, 4. Sketch T and T dash to confirm the rotation. So I'm going to start by sketching T, and then I'd like you to tell me the matrix we're multiplying by. So T looks like this. 2, 1 is here. 1, 4 is, I'm going to say here. And 3, 4 I'm going to say is here. And there's my triangle, and that's T. And I already know that if I rotate this 45 degrees about the origin, it's going to end up somewhere such that this angle, this line here is on an angle of 45 degrees, and it's probably going to go down like that. That's what I'm expecting to happen. That's about 45 degrees around the origin. So I expect to see my coordinates. I really am expecting this coordinate to still be in the first quadrant, probably actually up a bit higher, probably here, and these two to be in the second quadrant. But because it's 45 degrees, it's quite hard to see. So the only thing I can really use to confirm is that I know that this should now be on a slant of 45 degrees when I do that rotation. But I've got a bit of an idea of where it should go to. So we'll also sketch this once we've got our confirmed values. So can anybody tell me what is our matrix that we're going to be multiplying by? Cos 45. Sine 45, cos 45. And what's cos 45 equal to? One. No.
Is it? It's root 2 over.
1 over root 2.
Is it?
Root 2 over 2 is also the right answer. So either, that's just the rationalised third. So root 2 over 2 is probably better, but typically you'll see 1 over root 2 in this case. And this one's negative 1 over root 2. And this one is 1 over root 2. And this one is 1 over root 2. They're all in the first quadrant, so they're all positive, except obviously it's negative sine 45 in that cell 1, 2. And so there's our rotational matrices. And T dash will be equal to R times T, left-hand multiplication, which is 1 over root 2. You can see this is going to get messy. 1 over root 2, negative 1 over root 2, 1 over root 2.
Why is it negative?
Because that's what the formula is. It says cos theta, negative sine theta. And I'm going to multiply this by, I'm going to move this extension. Hold on a second, we'll talk about this extension. I'm going to do all three coordinates at once. So the coordinates were
1, 3, 2, 4, 4, 1.
1,
No, like a cross 1.
3, 2, 4, 4, 1. Yep. Okay, so there's my three coordinates at once. And if I apply this multiplication, my top cell will be 1 on root 2 times 1 plus negative 1 on root 2 times 4. Now the denominator is always going to be the same, so this is going to be pretty easy. All I have to do is work out, it'll be basically one of these minus one of these and all over root 2. So it's just going to be negative 3 on root 2, and then down the bottom I'll have 1 and 1, which makes 5 over root 2. And then I'll have 3 minus 4, so negative 1 on root 2. And then I'll have 3 and 4 makes 7 on root 2. And then I'll have 1, so 2 minus 1, so this will be just 1 on root 2. And then I'll have 1 and 1 that makes 3 on root 2, whatever those values are. And I don't know exactly what those values are, but I can work them out. What's 3 divided by root 2? Root 2 is about 1.4. 3 divided by 1.4, what's that? 2.1?
Yep, something like that.
Just go with it. So this is negative 2.1, comma 5 over root 2 is what? 3.5. 2.1, 3.5, which is about maybe here, maybe I was slightly off. And then negative 1 on root 2 is 0.7, negative 0.7. And then 7 on root 2, so that should actually be a bit lower. 7 on root 2, how many root 2s in 7? About 5. So it's about here.
4.9.
There we go. And then 1 on root 2 is 0.7, and 3 on root 2 is about 2.1 again. So 0.7, 2.1 is about here, and that's my rotated shape.
That's a right angle
It's just my poor drawing. Okay, if we get into Desmos, or if you use your graphic calculator to draw that, you'll see it's an exact 45-degree rotation, which I could muck around with now, but hopefully you will believe me. So that works. The extension here was, how do we rotate a known shape about a point x, comma, y? And the trick is that you have to get, let's say, for example, this isosceles triangle again, or even just this point. At the moment, I could rotate this point around 0, 0. But if I want to rotate the point around here, so say this is 2, 2, and this is 3, 1. Well, we need to work out what that value is relative to the origin. We've got to treat this like the origin. And to treat this like the origin, we shift that coordinate 3 this way and 1 down, which will put it over here. And you'll see this line here from the new coordinate, which will be t dash to the origin, is the same as that line. And then we apply our rotational matrices, whatever that is, it might be 90 degrees around to there. And then we get our new point and we shift it back. So we do a subtraction of 3 and 1, do the rotation, and then we shift it back up 3 and 1, and that will take it back to where it should be, the actual t dash, where that point is. That I would consider to be a highly complex procedure, which might come up in your exam, so know it.
Subtract the x and y values before the rotation and then add them back.
Because the rotation will only ever happen about the origin, so you have to make the rotation point into the origin.
Oh, that makes sense.
Yeah?